Today we're in Oxford and London to discuss a company whose origins were developed inside Oxford University and now over 10 years later, validated with FDA approval, is quickly penetrating the world of healthcare and medicine. Its name is OrganOx, and it's at the forefront of changing the way donor organs are preserved in the critical time between donation and transplantation. Amazing as it may seem, methods of preserving organs have changed little in the last 30 years. In fact, the British scientific journal Nature commented a few years ago, liver transplantation is a highly successful treatment, but it's severely limited by the shortage in donor organs, as many potential donor organs cannot be used because suboptimal livers do not tolerate conventional cold storage, and there is no reliable way to assess organ viability pre-operatively. OrganOx, however, has changed this. So the plan today is to capture both the immense medical innovation, why this is a lifeline for livers and potentially other organs, why FDA approval launches the company onto a new plane, and the potentially compelling investment opportunity for the company. And to help lead us through these steps, we have three world-class professionals. Professor Peter Friend, Professor of Transplantation at the University of Oxford and Chief Medical Officer and co-founder of OrganOx, Professor Constantin Coussios, Professor of Biomedical Engineering at Oxford, also co-founder of OrganOx, and Craig Marshall, CEO of OrganOx and previously MD of Siemens magnet technology business. So, welcome, gentlemen, today. I'd first like to retrace a few steps, and Peter, I'd like to start with you. How and why did this begin?
Well, I'm a transplant surgeon, so I've lived with the issue of the problems of organ donation and organ availability for the whole of my professional life. And I'm very, very conscious of the benefit that we don't do as transplant professionals, simply because there are more patients than there are donor organs. And that problem, of course, is getting worse. It is often said that transplantation is a victim of its own success. In other words, the results are so good that the indications for transplantation are getting greater. And although the donor numbers are increasing, the fact is that many of those donors are less ideal. They're older, they have other medical conditions which render the outcomes of transplantation less satisfactory, poorer. The technology, as you've mentioned in your introduction, for preserving organs, that's during the time between removal from the donor and transplantation into the recipient patient, is based on very, very, if you like, crude technology. The principle of cooling the organ down, the same principle as a domestic refrigerator, and actually even less sophisticated. And there are problems with cooling organs down. Sure, it reduces the rate of deterioration, but it doesn't stop it. And the really big problem we have is that when the organ is cool, when the organ, if you like, is in the refrigerator, it's not working and we can't test it. We don't know if it's going to function when it's transplanted. So that's the problem. And that was the challenge we set out to address.
Now, it's been observed that OrganOx was developed in order to solve a problem in search of a solution. But why had so many decades evolved where organ preservation and the thinking around it just hadn't changed?
The fluids that were used to perfuse through organs, the so-called preservation solutions, have improved since the beginning of transplantation, but as you mentioned, not over the last 30 years. So they're better than they were, but the principles are still the same. Back then, transplantation was largely involving high-quality organs, so young donors that didn't have anything else wrong with them. Now, because of demand, we're having to transplant organs that are less than ideal. Older donors with other conditions, cardiovascular, diabetes, obesity, factors which we know have a detrimental effect on the outcome of transplantation. So the problem is much greater than it was.
So I think that I read in some of your materials that 3,500 US donated organs aren't used. And so at what point, having conducted the surgery and knowing your area of expertise, did you start to think, what else? How? Just tell us how your thinking started to evolve.
it was a sort of paradigm shift that we're all brought up to think the really important thing in transplantation is cold. Keep the organ cold as long as you possibly can, and warm it up quickly when you transplant it. And we started to challenge that. So actually, the smart thing is to keep the organ functioning. So keep the organ in an environment which replicates its normal physiology as if it's in the body for as much of the time as we possibly can. So that's what we've done. It was actually easy enough to say this now. It was counterintuitive. It was not something which most people thought was very sensible. But of course, now we look back on it and say it was obvious.
So at this stage, I want to turn and bring in Professor Constantin Coussios. You're the Chief Technical Officer, and you actually are Professor of Biomedical Engineering. But to build the story, if I've understood it correctly, you actually were training to be an aeronautical engineer. So just explain to us what happened.
You're absolutely right, Simon. And in one word, what happened was a totally unexpected encounter with a different discipline in the form of Peter Friend, whom we've just spoken to. I had been training for 3 years to be an aeronautical engineer at the University of Cambridge. And I loved every aspect of the science and technology that underpinned it. But having had the very best opportunities a young engineer can hope for, the very best jobs, the very best internships, I quickly realized that for me, something was missing. What was missing was this direct human side to the research that I was hoping to undertake, this immediacy of impact on human health and human well-being. And that is not to say that that field of science wasn't thrilling and exciting in its own right. Just for me personally, I felt a call, a draw towards something that would have a more immediate impact on human health. And it was after having spent 3 very, very fulfilling years working towards aeronautical engineering that I met Peter Friend and one of his colleagues at Magdalen College, Cambridge, Geoffrey Lewins, who was an engineer. And they had conversations about this exciting potential of creating a device that could fool an organ into thinking it was still within the human body. That was a life-changing moment for me because what it resulted in was an opportunity for a young engineer to get involved with something which sounded completely outlandish at the time, not to study the flow of air around an aircraft wing, but to study the flow of blood through an essentially man-made circuit. And I remember visiting Peter and the laboratory team that had started keeping livers alive outside the body. And I will never forget the 19-year-old version of me holding in his hands for the very first time an organ completely disconnected from the body, completely disconnected from the nervous system, that was actually performing almost identically as if it was still in the person. And it was a moment of realization that there was a whole branch of engineering and technology waiting to be explored, one that supplemented, mimicked, and preserved biology for better therapeutic effect and therapeutic outcomes. And I've never looked back. That's all I've done for the last 25 years.
So for those of us who are not engineers and not medics, how would you just summarize the technological breakthrough that came along?
There were several, but I will focus on 3. The first is that depending on whether you're sleeping or whether you're eating, the flow rate through an organ, the liver in particular, can change by as much as a factor of 3 to 4. And what's remarkable about biology, I always like to say biology very rapidly teaches engineers a lesson in humility. Because engineers are raised to believe they can model, fix, and understand just about anything. And I think biology really throws a very important spanner in those works. So the first and most important challenge that was somewhat unexpected is the liver, as I said, will still do that when not connected to a nervous system or to the rest of the body. We don't fully understand how, we don't fully understand why, but it is capable of clamping down on letting blood flow through it unexpectedly, and then it is able to recover from that clamping down somewhat unexpectedly. So you might say it's a pretty obvious thing to do, to take an organ and try to replicate the environment it sees in the human body. As Peter alluded to, it had been attempted for 200 years prior, and no one had ever managed to get it to work for more than a few hours. And we believe the fundamental breakthrough was coming to grips with the importance of what we've called autoregulation. Creating an artificial system that fully enables an organ to choose its own blood supply, irrespective of whether it wants more blood or less blood, in the same way it is capable of doing in the human body. The second major challenge that we had to address is the fact that no one until this application came along had really had much of a reason to be flowing blood outside the body for tens of hours or even days without it going back through the patient. And one of the things that happens to blood when it goes through an artificial environment is the red blood cells get destroyed and they lose their ability to carry oxygen. So the second problem Peter, the team, and I had to solve was how to actually avoid excessive destruction of red blood cells over 24 hours so that you could actually develop a device that could be filled with blood once and then not touched again until the organ had to be disconnected. And that is the connection with aeronautical engineering. The science that underpins why red blood cells are destroyed is actually identical to the science that decides how much lift and how much drag an aircraft experiences it. So those skills, to my surprise, ended up being directly portable from supersonic jets and supersonic flow to these very, very low velocity blood flows that are experienced in human organs.
I watched this documentary on BBC Surgeons at the Edge of Life on liver transplants, and this is clearly way out of my area of expertise and competence. But with the wastage in organs, how have you been able now to pre-test these organs to be able to assess their efficacy?
The number you mentioned earlier, in terms of the proportion of organs that result in transplants, is what's driven this. Only about 2/3 of potentially eligible organ donors result in a liver transplant, and that's despite the fact there are large numbers of patients who are dying waiting for liver transplants. So it's really important that we can sort out the organs which really should not be transplanted with the ones that could be transplanted successfully to minimize any waste of a potentially successful transplant. And this is all about maintaining the organ in a normal functioning environment, as Constantin mentioned, it was still in the body. We can test the normal function of a liver to see if it's doing the normal things that livers normally do, which is producing proteins, producing bile, having blood flowing through it within limits that we recognize. So there are numerous ways of measuring whether a liver is functioning, and those are quite good surrogates, we have now discovered, for predicting how well that organ is going to perform when it's transplanted. And what we've discovered is that a very considerable proportion, in fact, current evidence suggests about 70% of organs that are declined actually potentially have the necessary function to be transplanted. Now, it's a little more complicated than that, as I'm sure you can imagine, but there is a very, very substantial target here to go after in terms of actually increasing the number of transplants. But the other advantage of what we're doing is that the preservation is better. It's not just giving us functional information about whether the organ is a good one or not a good one. It's actually saying we can take a poorer quality organ and add benefit to it in terms of function. It's a better quality of preservation, so we can preserve organs for longer. We can preserve intermediate quality organs so they function better. So it's not just a question of diagnosis; it's also a function of actual functional benefit.
Okay, so Constantin, I'd just like to ask the question, which is the costs of failure, because when organ transplants don't work, there are clearly very significant consequences. Can you just talk a little bit about, so we can frame the cost, frame the wider issues?
So there are significant challenges in a life-saving operation in making the wrong decision, and there are concerns on both sides of the Atlantic that lead to a conservative attitude towards which organs can be safely implanted. In fact, the reason why utilization isn't as optimal as it could be is threefold. One, there are certain organs which really cannot be preserved using conventional preservation techniques. Two, in many cases, it's logistics that get in the way. The fact, for example, that a hospital might have 3 organs arriving at the same time and only having 1 operating theater available. And 3, this risk aversion, which means that in the absence of a methodology that makes it possible to test organs before putting them in the patient, surgeons will be guided towards a naturally negative decision. And the type of normothermic machine perfusion technology which we have been able to develop addresses all 3. Based on the clinical evidence gathered to date, an organ sitting on a normothermic machine device will do things that can be measured. A liver will make bile, a kidney will make urine, which means you can provide the surgeon with concrete evidence of viability of the graft before the patient is even called in. The results also show that for those organs that are considered risky and perhaps not readily preservable using the current cold preservation techniques, we achieve better preservation. This is particularly true for fatty organs that come from patients that have accumulated fat, and organs that come from donors after cardiac death. And last but not least, we have been hugely pleased to see that in real-world deployment, the technology has addressed the many logistical challenges encountered in transplantation units. For example, in one territory, Austria, we have seen an almost eradication of nighttime operating. Because we now have windows of 24 hours to preserve these organs, it becomes possible to sequence them and align them for optimal utilization of resources in the healthcare sector, and most importantly, to give the maximum time to patients and their families to come in and have the transplant as desired.
So, Peter, just turning back to you, you started, and this whole movement was about dealing with livers. We're now talking about kidneys as well, with great attendant costs. Could you maybe just talk a little bit about that whole ecosystem?
Yes, the argument, if you like, the health economic argument for developing similar technology for kidney transplantation is even stronger. And that's because there is an existing technology which maintains patients on dialysis for often many, many years at huge cost, as well as with relatively compromised quality of life. So using UK numbers, a dialysis patient costs the NHS £30,000 per year recurrently. In the lifetime of a kidney transplant, it is estimated to save the NHS about £250,000. The numbers in this state are substantially higher than that, as are all healthcare costs. So the argument is very strong. We've developed a machine comparable to the liver, similar principle, different machine, which will have exactly the same objectives to prolong preservation, to improve the quality of preservation, and to allow assessment of the organ prior to transplantation, with exactly the same objectives of being able to transplant more organs with better results more safely. Now, we're at an earlier stage of this, but we have completed our early stage clinical trials with success. So we are very, very excited at the prospects that are coming as we roll out our program of development of the kidney device.
So that's a great time to start talking about the numbers. And before we dissect the numbers and evaluate the whole investment parameters, I'm turning to you, Craig Marshall. You're the CEO. Just first of all, explain your own piece in this jigsaw.
Sure. So it was a case of serendipity, actually, for me also, that I was introduced to OrganOx. At the time, I was, as you said, I was with Siemens, doing a piece of pro bono work at the university, and by chance, I was introduced to Constantin. I was singularly impressed by Constantin and blown away with what was being attempted here. I then later met Peter, and I then realized this is what I really would like to do for the rest of my career. And thankfully, I got the position, so I took over as the CEO in late 2016, and I've never looked back.
That's great. Lots of brilliant inventions are born in universities. Lots, however, don't make it to the path of monetization. And so let's just put the spotlight here on this particular piece, mapping, if you like, the invention to income. And just talk us through the commercialization process.
There are really 4 key steps. Step 1 is a first-in-human trial to prove the technology does what it's supposed to do, safely and efficaciously. Step 2 is to then create a product which you want to take forwards onto the market, and to prove that in a randomized clinical trial. We did that in Europe, and we've now most recently done that in the US. Step 3 is to present the data to the regulatory bodies, the FDA in the US and the MHRA in the UK, to generate the CE mark here in Europe and PMA approval in the US. And then fourthly, it's a question of then taking that product onto the market and demonstrating the value proposition in the clinical setting, which I'm happy to say we're doing very effectively now on both sides of the Atlantic.
I mean, for any company in your business, FDA approval, that's, I suppose, the ultimate step. How did that change the whole thrust of OrganOx?
So the FDA approval is the single largest value inflection for a medtech company. It's a rigorous, protracted process. We committed to that for many years, and now having achieved this, it's clearly we're able to do far more. So, for example, in terms of recruiting very high caliber talent into the US in the wake of this has been critical to the commercial success, I would argue. Getting the instant recognition of the KOLs is clear. So right now there's just OrganOx and one other company that have achieved this milestone into the US market. We're in a very elite group right now, and it's entirely down to merit. Got there.
Now, can you also give us a sense of the size of the market, which will obviously then drive the sense of the revenue opportunity?
Sure. So liver transplantation in the US currently is about, from deceased donors, about 9,000 cases a year. In terms of market valuation, it's approaching a billion total addressable market in the US. What we are seeing now is the rapid adoption of our technology, primarily due to the opportunity to increase the number of transplants, as Peters and Constantin have described. But there's a second driver, and the second driver is one of our customers in the UK actually calls this a time machine. So we can put the clock on hold with this technology. And that's driving the adoption in certain centers, not only now in Europe, but also in the US, where surgeon burnout is acknowledged as a real issue by the American Society of Transplant Surgeons. So having surgeons who can take a break between successive surgeries is becoming increasingly important. And that's a problem that we can really help with.
So, Craig, we're talking livers, we're talking about this significant opportunity, but all of your work is pushing out the frontiers into other connected disciplines. Can you just give us a sense of what those are and those markets?
Sure. And I'd like to just acknowledge the power of OrganOx in many respects is down to the fact we've got the eminent co-founders in Peter and Constantin having a foot in Oxford University as well as in the company. And that's benefiting the company enormously. And we're able to then recognize the platform that we've developed here. The most obvious opportunity for this platform is within transplantation, but as you allude to, there are other applications which are in our pipeline. Those are also exploiting this isolated organ perfusion proprietary technology we have, whereby there are, for example, patients who will never be able to receive a transplant, but nonetheless have end-stage organ failure, for which we can help in a patient-connected manner. So this is opening up a much larger market, in fact, where patients who might have an acute liver failure who won't get a transplant may well be treated through being connected to one of our products in the future.
I just want to pick up on something you said, because as we said at the beginning, this began within the Oxford University system. Just help us understand, what is it that Oxford, beyond its name and reputation, gives to this whole enterprise?
Well, one interesting consequence of working within Oxford, or as so closely associated with Oxford University, is what I would sometimes describe as the Oxford University diaspora. So there are certain DPhil students who are attracted to come to Oxford to be supervised by Constantin and by Peter, who later go on to the US or go into Australia or go into Canada. All of those are real examples where, through the relationships fostered within Oxford University, OrganOx has been able to leverage that effect, and they've pulled our technology into their new centres without having to have an expensive marketing and sales arm, because of this strong academic connection back to Oxford. It's really helped us establish this business in many territories, actually.
So we're going to come back to the capital and ownership structure in a minute, but I will just note Oxford University, I think, own 10% of OrganOx still today. But just back to the numbers, again, the history for investors is of lots of great creations that sucked up lots of capital on the journey to being revenue positive. If I've understood our conversations and your work, you're quite close to becoming cash flow positive. Tell us a little bit about how you see this whole revenue trajectory.
Sure. So that value inflection that I referred to, which was the FDA approval, is mirrored with the revenue inflection for this company. So within the next fiscal year, we will become cash flow positive. We're on track for revenues north of 10 million this year. Today, largely British. The Business Growth Fund is the largest single investor. The university has a double-digit stake, and then there's a couple of VCs that are one Oxford Investment Consultants that was founded by George Robinson and Longwall Ventures. These have been very supportive venture capitalists who've been with us along our journey. And if it wasn't for that level of support, unwavering support, we wouldn't have achieved what we have.
And certainly, I'm aware that George Robinson has been a key agent in at important times as your evolution has taken place, and is a terrific advocate for what you're doing. Craig, let's just talk about the 10-year runway. And maybe this is going to be a little bit sort of general, but a clear competence and expertise that's proven and validated, a medtech company that is evolving quite quickly. What are the opportunities for a company like OrganOx that you think fit, taking that 10-year view?
So the 10-year view really is to build on what Peter has described at a high level, and namely within transplantation to exploit this technology to increasingly treat organs prior to transplantation. The extreme version of that is to personalize the organs for the intended recipient. beyond transplantation, there are other opportunities for this platform technology, which is really can be described as isolated organ perfusion, which actually may not be constrained by the supply of a donor organ. Those are very exciting mid to long-term potentials for our company. So we have a rather full pipeline of products in development, which certainly over the next 5-10 years will be coming onto the market and helping to expand our impact clinically and commercially.
Clearly a very exciting story, but you don't exist in a vacuum. Just give us a sense of what the competitive landscape looks like.
So I'd say it's very vibrant, but it's probably a good thing. We're driving to be able to prove ourselves in a competitive landscape is a great stress test for our business, and we are certainly doing that. The entry barriers are very large to get onto the market in the US. Currently, there is ourselves and one other competitor that have gone through this multi-million-dollar, multi-year program to get onto the market. There are others that are following our lead in that sense, and we're establishing ourselves to be a very valuable business in the US and now in a dozen countries across Europe.
And if you were to describe your distinctive competitive advantage, how would you summarize it?
On a product level, it's very much down to the fact that by design, this product is an automated product which very much reduces the scope for operator variation, which is so important clinically. So we have taken out of the operator's sphere of influence how this perfusion takes place. And that's very much down to the engineering systems that Peter and Constantin have co-developed over more than a decade together. And we've harnessed all of that into a product which offers a very repeatable perfusion, which is massively valuable in a clinical setting.
So Craig, then finally, just give us a sense of the trajectory, the possible trajectory for your company.
So within organ transplantation, liver and kidney alone, that's around a $1 billion opportunity. The other opportunities outside of transplantation are probably an order of magnitude greater. One of those we've already had a press release around is in drug testing, for example, where we are using our proprietary technology to great effect in candidate screening.
So one of the things that intrigues me is that in this evolution from a theoretical technology to a practical, approved, thriving business is you start to get business challenges. Now, you've had the benefit of working at a world-class company like Siemens. What would you say what would you say Siemens has taught you most that you want to bring to OrganOx as a business?
So I think it's the long-term vision. It's having running the business with 3 horizons, which we do at OrganOx. We call that today, tomorrow, future. So we focus our efforts on the product that's on the market. We separately focus on the next generation and how that's going to shape the market. And then there's the blue sky stuff. And it's important that we never lose sight of that. And we are not limited in our thinking whatsoever in those longer term opportunities. So today is right now, tomorrow is the next 3 years, and the future is out to the 10-year horizon. That's precisely how Siemens runs its business. That philosophy is what I've brought into OrganOx, and we run that. That's what we live and die by.
And the other important area that's getting more attention in today's world is, of course, oversight, governance, and a well-rounded board. I've looked at your board. It's got some very interesting people that have joined, including Ernst Stooge, who has a long history with Medtronic and Abbott Labs, and I believe has been involved in a number of very successful business developments and sales. Just tell me a little bit about board composition.
I've learned a tremendous amount from Ern. what we have now in the board is a healthy balance of the insiders. That's obviously myself, Peter, Constantin, and our CFO, Graham Yateman. The independents, which is really Ern, and most recently John Liddycote, who was ex-EVP from Medtronic, Juliet, and we've got the investors as well, the VC investors, including George Robinson, who are all on our board. So we've got a healthy balance now of those independents, investors, and insiders.
Great. And one thing that struck me doing my research, and this comes back to why your FDA approval was so important, is that, am I right in saying that there are other countries, such as Switzerland, that is accepting US approval for medical devices? So just tell me a little bit about how the rest of the world views progress, such as the progress you've had.
From having had the experience of getting onto the market in Europe and in the US with the FDA, I think it's fair to say many companies are now at the start of their journey are contemplating going onto the US market before Europe, which was not the case. That was not the received wisdom 10 years ago. Having got onto the market in the US, then certainly other countries are very receptive to understand and accept the filings that we have had to make in the US as part of their submissions.
And Constantin, I know you're very familiar with this.
Absolutely. We like all medtech companies, we have had to deal with a very rapidly changing landscape from a regulatory perspective in Europe versus a reasonably constant and mature landscape in North America. And I think this has been a very challenging time to be straddling both sides of the Atlantic for any company. In the UK, the additional complexities brought by Brexit have made this ecosystem slightly challenging. In the FDA, however, we have found a very tough, but also very dependable partner in working towards that regulatory submission. And I am absolutely delighted that the outcome was the outcome it was. We are, as Craig mentioned, one of a very small club of Class 2 or Class 3 medical devices to have achieved such regulatory approval. If anything needs to be improved about our ecosystem in the UK, is actually enabling studies to take place that prioritize regulatory approval not only in Europe, but also in the US almost simultaneously. And we do believe that is achievable in the new regulatory environment that we're in.
But if I were to ask each of you in turn, starting with Peter, essentially my question is, why does this matter?
Let me illustrate that by some data. If you're a patient in the United States and you need a liver transplant and you're placed on the national waiting list for a liver transplant, the chance of you receiving that liver transplant in the next 3 years is about 60%. And there's a very strong probability that you will not be alive by that stage, that you will have died on the waiting list, or that your name will have been taken off the waiting list because you're now too sick to remain there. That's a huge challenge, and that's in the best funded healthcare system in the world. So the technology we've developed is designed to address that very, very powerful anomaly in the healthcare systems around the world.
Constantin?
What I would like to convey to supplement that is the extraordinary sense of excitement about the transformative ability of this technology. As Peter says, it ranges from making the untransplantable transplantable to actually opening up this ability to keep organs alive with minimal human supervision to a whole range of spaces, ranging from pharmaceutical development to patient-connected applications that have never been explored previously. And I think what this device will achieve will transcend the field of transplantation in the next decade and touch almost every area of medicine we can today think of.
And I turn finally to you, Craig.
So I think we're just scratching the surface, quite honestly, of what we are, what we've developed. When you imagine adjacent fields, so medtech adjacent to biotech. There's a whole opportunity there, which is completely untapped right now. So I think over the coming decades, we will see isolated organ perfusion being the sort of the crucible of a whole paradigm shift in what's made possible. And I'm just so thrilled to be a part of that.
So, wearing my investor cap, it seems that we have a fusion of passion, need, and commercialization. The strapline that your company is saving lives by making every donated organ count has real resonance. Clearly, this is a British company that's getting a lot of attention globally, and the opportunities, current and future, are incredibly exciting. So it's been just a huge privilege for me to understand what you're doing and to be in the company of people who really are making a difference to the world. But I'm not going to let you all go just that quickly, because one of the things about the Money Maze podcast is that the final questions are generally very well received. We have listeners, professional investors, and young people as well. And one of the questions we like to ask, and you don't all have to ask it, but, advice for young people thinking about the world of medicine and, yes, engineering. What might be the one thing that you think is most relevant from the time in your domains? Constantin.
I would like to emphasize the importance of multidisciplinarity. I think we live in an era where all of the great inventions sit somewhere on boundaries and interfaces. And for me, case in point was my life-changing encounter with Peter. And what I would like to encourage every aspiring technological or medical researcher there is to take the time to talk, listen, understand, and translate conversations and approaches from other fields. Because somewhere in one of those conversations is hiding the next game-changing OrganOx.
Really following on from that, this is why universities are so powerful, because of course they bring together disciplines. We have conversations, we meet each other, we find solutions that we would never have dreamt of. But from my own perspective, the young surgeons who spend time working on this research in the lab, they find it completely fascinating, because this is finding new ways of doing things. Most of medicine is being taught how to do things the way other people have done them before. It's about learning how to do things, doing what you're told. This is all about breaking paradigms. It's about finding new ways of doing things, addressing problems that have not been addressed before. And it's a fantastically exciting environment for bright young medical professionals to go into.
So I think it's just really how exciting this is to be at the crossroads between engineering and medicine. It's a great place to exist, and I would encourage young people to be curious about that space.
So we've talked a little bit about the investors who have been so influential in OrganOx's development. Different investors suit different styles and companies, and maybe you could just reflect on the characteristics that make for the optimal investor for a company such as yours. Peter.
I'm going to start by saying that I'm hugely grateful to our investors right from the beginning, very aware of the risk taken by investors and about the faith which investors place in those of us that start spin-out companies, startup companies. And it is, of course, absolutely critical. It's simply, we would not be here today if those individuals hadn't had the faith to invest substantial amounts of money in something which we promised would work, but for which we, of course, at that stage had no proof. So really important, hugely valuable part of the OrganOx story. Very aware of it all the time.
Okay, and Constantin, just turning to you and then also thinking about the next group of investors who may want to be associated with you.
Like Peter, I share the gratitude for what has been achieved to date with the support of our investors. I also think diversity and quantum of capital are two areas where the UK ecosystem would benefit hugely from. And let me explain what I mean by that. I think first of all, as we move more, there is no doubt that in OrganOx's history, we could have accelerated our progress with slightly greater quantums of capital in that all critical mid-period phase of the company. And I think there is no doubt that sitting where we are here today, there is plenty of opportunity to accelerate some of these more futuristic developments we were discussing with you today with that different quantum of capital and investment. Investors also bring much more to the party than capital. And I think where we have been very keen to learn and grow our ecosystem is in also getting the local knowledge, the regional knowledge, the territorial knowledge that comes from investors with a greater focus towards North America or towards Asia, which are massive potential future application markets for the OrganOx technology.
Yes, and I think that was something that Kate Bingham said in an earlier podcast that we did, where the really good investors are the ones who partner with the business rather than simply as suppliers of capital.
Yeah, absolutely.